Today's lesson is Graphing Proportional Relationships, Lesson 4.3. So direct variation is a term we use when two quantities, x and y, are proportional. The relationship can be represented by the direct variation equation y equals mx, where m is the constant of proportionality. So you see on the graph that the graph of y equals mx is a line with a slope of m that passes through the origin. So we have talked about an equation that's similar to this. So y equals mx, there is no plus or minus b on the end for the y-intercept. That is because that it has to go through the origin. So straight line has to pass through the origin. Remember, m is the slope. The cost y in dollars for x gigabytes of data on an internet plan is represented by y equals 12x. Graph this equation and interpret the slope. So we're going to quickly work on graphing the equation. So I'm going to rough sketch a graph in here, and then we will get started. All right, you can see that I've started with my graph. Again, a rough sketch here is fine. So the cost y in dollars, so I knew my y-axis would be labeled with dollars for x gigabytes. So I labeled my x-axis with gigabytes of data on an internet plan is represented by y equals 12x. Now, we can graph and interpret the slope. So we know that there is no plus or minus b, so we must start at the origin at 0. We know that our slope is 12. So from this point, the origin, we go up 12 units over 1 unit. Up 12 units over 1 unit. And we can draw a straight line through these points. Now, interpret the slope. What does it mean? So we can see that $12 for 1 gigabyte. We can use our information from this table or this coordinate plane to answer this. So we could say that each gigabyte costs $12. And we can see that that is the same for each point on our line. We can see here that we have $24 for 2 gigabytes. And if we kept going, it would be the same broken down for each time, the same unit cost, $12 for each. The weight of an object on Titan, one of Saturn's moons, is proportional to the weight x of the object on Earth. An object that weighs 105 pounds on Earth would weigh 15 pounds on Titan. Now, if we go back, we see that Titan's weight is y, and the weight on Earth is x. So we need to start by writing an equation in y equals mx form. So we know that we're going to need y equals mx. We don't know what the slope is, but we do know what y is and what x is. So 105 pounds on Earth is x. 15 pounds on Titan is y. So right now we have 15 equals m times 105. In order to find the equation, we need to find m because we need y equals a number and then x. So in order to solve for m, we can divide both sides by 105, just like we were going to solve an equation. 105 divided by 105 cancels and we're left with m. 15 divided by 105, we can divide both of those by 15 and we get 1 over 7, 1/7. So we can write an equation that says y equals 1/7 x because we know that m is 1/7. The benefit of doing this is we can then use this to make a prediction or give a cost based on another point in time on that line. So here, that's what we're going to do. How much would a spacecraft that weighs 3,500 kilograms on Earth weigh on Titan? We know that from before, Earth is x. So we're going to put 3,500 in for x. So y equals 1/7 x, and we are replacing x with the 3,500. Go ahead and try to solve this now. As you've done that, 1 times 3,500 is 3,500. 7 times 1 is 7. We know that 3,500 can be evenly divisible by 7 to give us 500. So the weight on Titan would be 500 kilograms. The table shows the distance y in meters that a T-bar ski lift travels in x seconds. Compare its speed to the ski lifts in example 3. So it says the table shows the T-bar. And here we have a 4-person lift and a 2-person lift. So the first thing that we need to identify is that for each second, the T-bar goes 2¼ meters. So we're going to kind of compare these. So T-bar is 2¼ or 2.25 meters per second. Now, looking at the 4-person lift, where does it cross at the slope of 1? So we have, or since it doesn't cross exactly at 1, we might have to go up a little ways. So it looks like here it probably crosses at a perfect corner. So 10 meters in 4 seconds is equal to 2.5 meters per second. We can divide these. 10 divided by 4 is 2.5. So 2.5 meters per second. And again, I found a place where my line crossed at a perfect corner. Now, on my blue line, I can see that it crosses at a perfect corner here. So 4 meters in 2 seconds. So my 2-person lift, 4 meters in 2 seconds. Again, divide 2 meters per second. So now we want to compare them. So we know what they all are. How can we compare them? So the T-bar moves 2.25 meters per second, which is slower than the 4-person lift because 2.5 meters would be faster. It's going further in the same amount of time, but faster than the 2-person lift. So the T-bar lift travels 2.25 meters per second, which is faster than the 2-person lift and slower than the 4-person lift. Now, we can use these proportional relationships to compare things. So we're using the proportional relationships to see which one is the fastest or how they compare to each other. Now you can see that these are all proportional relationships and show direct variation because they form straight lines and pass through the origin at the 0, 0.